My name is Riley Berton. I'm a principal engineer here at AppNexus. I run the team we call DERP. And as you probably have guessed so far, I'm pretty good at naming things. DERP stands for Data Engineering Real-Time Platform, which is sort of slightly different than the existing data engineering team that had existed at AppNexus prior. I'm here to talk to you about log-level data, which is one of my favorite topics and hopefully one of your favorite topics. I'm going to cover sort of what happens on our platform when an impression is served, the existing log-level feed that you guys, probably many of you consume and know about, sort of the tech behind that, what the problems are with that model, and the new streaming variant that we are sort of announcing, I guess. But before we get to that, I want to have a little bit of fun. If you have a laptop open or a cell phone, we're going to have a little bit of fun first. I would like to introduce my colleague Andrew Sweeney, who is the Director of Engineering for the Auction Module 4.
Okay, so what we're going to do is we're going to actually start with a little game. So I won't tell you exactly what the game looks like or the goal of the game, but the whole point is you'll see someone's face on the screen. It's mobile enabled, so you can either use your phone or a laptop, and you'll move the face left or right, and you'll see little missiles that will be fired. And the point is to actually blow up the ads that are falling down from the sky, and the score you'll get will actually be the CPM of the ad or the creative that you actually blew up. And don't get touched. If you get touched, you lose.
Ready? Now I'm going to give you guys a URL to go to if you want to play along. Are you ready? Go to skyfall.adnxs.net to play if you would like to. I'm going to actually play along from the stage for those of you who don't care to play so you can see what it looks like.
So the really interesting thing about this game is these are actually creatives that were served on our platform seconds ago. Literally seconds ago. These were actually served on our platform, rendered them, and now you're shooting them in the game, and these CPM values are all real. So this is actually coming off of the real-time log-level stream data. So it's a really useful demonstration of why log-level streaming is actually beneficial for our platform.
All right, my job. So, anybody beat my score? What did I get?
42 points.
42 points. Anybody beat my score? No?
No one beat 42 points?
I'm apparently the expert. All right. So, thank you, Sweeney. Thank you very much. So, that was incredibly silly. But the point was not silliness. A lot of things have to happen. This is sort of the top of the tip of the iceberg, right? When we're talking about ad technology. Everything that makes these ads actually work is this huge amount of infrastructure underneath the water that we're not really exposed to. And I'm going to talk you through how that works. But in order to get through that, I have to talk about what happens when an ad is served on our platform. So this is the simple case where we have a user tag on page, right? They make a call to what we call our impression bus. Some of you might be familiar with this. The impression bus will construct a bid request, right? And fire this off to a set of bidders on our platform. Those bidders all respond in 3 with a bid response, right? The impression bus will then rank them, pick the winner, right? It's at this point that the data journey of an ad serve actually starts, right? Number 4 here is where the impression bus logs out a bit of information about the auction. It contains all the sell-side information, right? And effectively the winning price. That gets logged out to a system we call PackRight, and I will cover that in detail in a few minutes. After it logs out information about this, it will send notify to the bidder. So we notify both winners and losers on our platform. So we will send out most of you, or all of you except one, lost, and one bidder won the auction, right? If that bidder happens to be our console bidder, we will then log out in 6 the information about the buy side of the transaction, right? And that's what we call a bid row internally. And these all flow through to PackRight, and I'll cover that in a minute. Now that's the simple case. The more complicated case is when we have sort of external supply, some sort of SSP. right? So in this case, 1, 2, 3, and 4 are the same. We still get an add request, we get an auction that we create, we get some responses, we log out the fact of that auction. However, now we have to wait, because we have to wait for the SSP to tell us if we actually won, right? So at some point in the future, and that future can be very long, the SSP will send 5, which is your win notification, you won, right? And it's at this point that the impression bus will turn around and notify the bidders on our platform whether you won or lost based on that auction, right? The bidder will log out the buy-side information, and the impost will log out a new thing in 8, which is basically the win notification. So then we have not just 2 pieces of information to join about the transaction, but 3 pieces of information to join to make the transaction whole on our platform. And these are the artifacts. If you've consumed our log level feed, these are the artifacts that get joined together that makes your impression standard log level data feed. Right? These are the things that you're getting all joined together with some math to calculate the fields. So one of the problems here is time delay. Win notifications can be time delayed. I don't know how many of you operate on the Facebook exchange, but they actually document 12 hours is their wait time for a win notification. And it makes sense, because they don't like to send win notifications till the ad shows, right? So it could be 10 scrolls down the page somewhere there's an ad. They conduct this auction at the beginning and load up all these ads. And then they don't actually send the win notification on the platform until that ad is displayed in your newsfeed. So you can imagine someone's going to work, they're scrolling down the newsfeed, and then they close their laptop and they go to work all day. They get home at 8 p.m., they open their laptop and they scroll down further, and then that ad shows. And then we get a win notification. So you've got to join this thing that happened 8 hours ago, which is a lot of data, with something that happens relatively recently, like now. And then when you're doing this 120 billion times a day, that's a lot to keep track of. So it appears to fit nicely for a MapReduce problem, right? We put all these things in a bucket, we go over the bucket, join them all together, and then we have an answer. The problem with that is the closing of the bucket. When do you know, how long do you have to wait till you know the bucket is done? If you're waiting 12 hours and you're collecting, effectively 60 billion impressions in that bucket to join, that's a lot of work to do. You've got to have quite the HDFS cluster to pull that off with any kind of time sensitivity. So the other problem with this join is it's also extraordinarily sparse. So most exchanges do not do loss notifications. So back to the Facebook example, they won't tell you if you lose, they'll just tell you if you win. So if you lose, it's effectively a timeout. You waited 12 hours, you never got the win, so you have to guess who lost, right? This makes the join very sparse. If we had a bunch of easy to join information and loss notifications were flying continuously, right, it's not that hard of a problem, you just do it as you go. But since you have to wait, that's what makes it particularly difficult and sticky, nasty problem. So, again, on the sparse joins, the top, the green line would be impressions that come in per minute. The blue line would be bid rows that match those impressions, so it's a little bit sparse already. The red line at the bottom there is win notifications, right? Somewhere in this mix, this sea of numbers, are actual wins, actual auctions that you won on the platform. And it's the join of these 3 pieces of information that actually spits out the win. Not every auction gets a red line, right? Which makes it harder. So this is the existing feed, right? This is the one that you're used to. We get sell-side information artifacts from the inbox. We get buy-side information artifacts from the console bidder. These flow through the system called PackRight, who will then log this information out to HDFS in the existing feed. Then we have these series of MapReduce jobs that all run in serial to do one big join, another separation by member, split it up into buckets that go per member, into hourly buckets, and then you have your standard log level feed that you get via API, and we point you at an HDFS bucket, and you download it, and that's it. That's how the feed works. PackRight. So PackRight is our own homegrown data router that sort of predates me at AppNexus. Has been around since the dawn of time, I think. It is a buffer and forward from non-primary data centers. So we've got 5 data centers, and I'll cover them in a minute. And PackRight basically takes all the traffic over HTTP post, snappy compressed, what is now protobuf records, or not exactly protobuf records. I'll cover that in a second. Its primary job is to take this information, repackage it, send it on to primary data centers, and log it out to disk, right? Then we have another system, which is part of the data pipeline tasks, which pick up these files, put them in HDFS. The important thing about PackRight is that it parses and validates every single row it sees, which is quite a high volume of rows. So I was talking about our data centers. We have, that slide was really hard to see, huh? Okay, that's the world. The blue sort of, LA and New York are two primary data centers. So New York would be where we do most of our data processing. We have a hot setup where we do HCFS or MapReduce stuff in both New York and LA. And if you're interested in MapReduce and sort of huge data at scale, definitely after this talk, go see Ersin and Swap and they'll talk about how we actually do this. It's actually quite amazing. We have Amsterdam and Frankfurt, which are close by here. Those are slave data centers, so they don't actually store anything on disk at all. They just forward everything to New York. We use disk backup, and we have another program that's sort of part of the PackRight package called repackd. So if post failures happen, we go to local disk, and then we have another program that picks these up and sends them along. And then we have a lone data center in Singapore, which actually sends to LA, and LA and New York send to each other, right? So everything is fully redundant in both data centers. We don't lose any data. But when I was making this slide, and I'm sorry you can't see the world because it didn't turn out like I thought. But I was making this slide and I noticed the New York, Amsterdam, Frankfurt path looks a little bit like, is anybody a Family Guy fan? No? Does that look like Stewie's head? Does look like Stewie's head. I'm not sure why, but he's pointing to Italy. It must mean something. Okay, so some metrics on PackRight. PackRight worldwide will send that green line roughly every day, which is about, this is per minute, so it's about 1.5 billion rows per minute on our platform, fly around the PackRight. At peak, we do that kind of traffic, and then the smaller data centers, you can see here at the bottom, I think brown is Singapore, and red might be Frankfurt, something like that. So there's a lot of individual rows. They're variable in size. Some of them are big, 800 bytes or more per row. Some of them are really, really small, 20 bytes. We compress these down to about 3.5 million-ish at peak requests. So these are individual HTTP posts that actually send this data. And that is about 60 gigabytes per minute. And this is compressed data. So we're sending maybe 128K buffers at a time. Those are compressed down using Snappy, and then we fire them over the wire. So there's a bit of a trade-off here between throughput and latency. And we'll talk about that too. So if we really, really wanted to solve the latency problem, really, really solve it, we would do individual message delivery, right? We would say, fire them off, get acknowledgement for everyone, and they would be extremely low latency, as close as we can get to wire speed, right? But that has a pretty bad throughput when you have to wait for acknowledgements for every message sent. So we don't do that. We do a sort of a mix, right? Where we take buffers of a size that's not too big, but not too small, so we get a pretty good compression ratio. And we fall back to a max weight, which means, yeah, we want to get to 128K before we send a buffer, but if it's been too long, 30 seconds, 60 seconds, whatever it is, send that buffer anyway, no matter how full it is. This way, we have a pretty good trade-off there. We do compress everything that we send over the wire. It's currently Snappy. Zip or LZH4 were looked at. Snappy sort of gives us the best combination of compression and speed for CPU power. We actually run all of the PackRight traffic throughout the world on 50 machines. So it's actually fairly efficient to do this. So more about how they communicate. I'm just going to grab some more because it's trying to go. Excuse me, when I started here a little bit over 2 years ago, everything communicated with ASCII tab separated values. Anybody else use ASCII tab separated in any of the things they do? Please stop doing it if you're doing it. You don't have to raise your hand because it's embarrassing, but don't do it. So here's what happens. We get highly concurrent applications that run on our platform. We saturate every core that we can. These introduce all kinds of interesting concurrency issues, especially when you're dealing with shared buffers. And what can happen with ASCII TSV is we get people right into the same buffer. And The interesting thing of being sort of schemaless is that it's difficult to disambiguate these sort of mistakes later on because they have a schema, but they don't. You could easily mistakenly write a number that looks like the number it should be there, but it's the wrong number for the wrong campaign, right? And you could intermingle data in a very, very bad way. On top of that, it's really, really horrible to parse ASCII, right? If you're doing this 1.5 billion times a minute, actually parsing that number, turning it back into a double, so I can do some math on it, and then putting it back into ASCII is extraordinarily expensive. You'd be surprised how much CPU time that eats, just doing that back and forth, back and forth. Some of you who might use JSON probably have experienced this, how expensive it is to parse JSON continuously. It's pretty helpful. So one of the things that came up here is when we sort of made this realization that ASCII TSV is terrible, is the downstream consumers of any data format can disagree, right? So we can have a data pipeline that wants to consume protobuf, and they do. And we can have a real-time ad serving platform that wants to communicate in something faster. Because even parsing protobuf is too expensive, really, at our scale. So we want something that's more like a memcopy for the real-time platform. But we want to use sort of maybe more acceptable formats elsewhere, like protobuf or Avro, or even JSON, right? So what we did was we created something called AppNexus. Now this started out as just a way to deal with logging and the lack of schemas in logging, and the lack of easy transitioning or transcoding between formats in logging. It's since grown to sort of take over the platform. Now we do almost all of our communication, I think, as AppNexus. And what this is code generation. So we make a JSON schema that defines a message. This can be arbitrarily complex with nested messages and lists of nested messages and all kinds of crazy stuff, right? And then we use a Python program with a bunch of templating to generate C code, right? And we have one single API to get back and forth between our formats. So now we can send buffers of this stuff on the wire. PackRight can parse it and then spit out something else. And it's all one API to our platform, which is pretty fantastic. So we actually do this in production. We have impression buses and bidders sending out x86 memory structures on the wire, just full speed, right? PackRight will parse every one of these and validate to make sure that there's nothing crazy going on. And then it will transcode it to protobuf, write it on disk. We've now gotten that expense, that protobuf expense of doing that serialization, deserialization, out of the real-time platform, and we pushed it off into PackRight, which is not in the fast path. And we still get the benefit of having protobuf schemas that we can communicate with you guys with, or with each other with, right? So this is another slide of how it works. We get JSON, we get Python, we spit out C code for protobuf, Avro, JSON native, tab separated. We still actually have support for TSV in AppNexus. If we had to, we can spit out ASCII rows, but it's banned, strictly banned. Firewall events. So the standard log level data feed. Now so you have some context. We're going to get back to the standard log level feed. So what we provide today, this is the feed that you're all used to. We give you transacted impressions, clicks, conversions, views, and click trackers. They're delivered, this is the important stat, on average, 110 minutes after the ad is served. That means the ad serves at the beginning of an hour, the hour ends, and at the end of the next hour, you can actually get it, which is kind of hard to do anything real time with. They're made available in hourly buckets, and it's currently, again, the evil word, ASCII TSV data. So why is this a problem? Well, the 2-hour delay makes real-time decisions basically impossible. You can't know what's happening right now, or you couldn't know what's happening right now on our platform. So if you have real-time spend changes you want to make, or any other real-time decision, you can't do it with any kind of visibility. You probably do it yourself, set up your own pixels and get some things fire and do it yourself, but it's actually really hard when you have the kind of scale that we have to deal with. So the batch-oriented process here preempts the ability to stream process. So if you're into the herons, the storms, the Spark streamings, the whatever, for processing data in streaming fashion, you actually can't do it right now. You have to get this dump and then restream it internally to yourself and then do your stream processing. But what's the point if you're already getting a batch? ASCII again, my nemesis. It's quite expensive to parse in bulk, and it lacks type safety. We've already covered these things. I'm just reiterating. And the lack of structured data, the lack of schematic data is hard to make tooling for. So when you have generic protobuf messages or some kind of schema, right, we can tool around how we translate these things. This is what AN message is, a tool to translate between types, to do all kinds of interesting things, generically, right? So what's the solution? That's a great question. 2-hour delay for data. Well, it's a blank. I don't know what's happening to the slide. Okay. We stream process everything. This is the solution. So instead of having this bucket concept, where we put everything in a bucket, and then process that bucket, and then produce some kind of output, we just deal with events as they arrive. This means things are free to arrive at any time, 12 hours later, and we will match it to the original auction and spit out data at that moment. So it sort of reverses the concept of when did this impression happen? Did the impression happen when the auction happened, or did the impression happen when the win notification came in? I would argue that it's when the win notification comes in, because that's when it happened, right? This reverses that. Batch download is a problem. I don't know what's going on with these slides. Sorry. It's just really slow. So instead of batch download, we give you a fire hose, right? This means all the events as they happen streamed directly to you in real time, right? So the ads that fall from the sky, they would show up in your system seconds after they happen on the platform. If this is tab separated ASCII, that's our timestamp format from the beginning. If tab separated ASCII is a problem, which it is, come on slides, oops, now see? Go to something schematic. So the new feed that you will get is actually a protobuf record, right? It contains all the fields that you would care about in your existing log level data feed. It just adds protobuf, and they're all typed, right? And they all have reasonable defaults, and it all makes sense, and it's something that everyone can easily understand. So how does this work? How do we do this? Well, I'm going to go through the pieces. We use Kafka. Anyone else here use Kafka now in anything that you work on? Yeah? Nice. It's good to see. For those of you who don't know what it is, it's a durable pub sub message queue. You can think of it as an append-only log with consumer-maintained offsets, right? So it's clustered with high availability and replication, right? And the important point here is the consumer maintains the offset, and so therefore it deals with the slow subscriber problem, right? So we can just spew data into this thing. Someone else can read at their own pace back into their log for as long as we keep it, right? And it's actually very nice. It scales very, very nicely for our use cases so far. The second part, so PackRight in this world used to just stream things to disk, right? They would go off into HDFS and be processed. Now PackRight has a new functionality where we can split the streams, send one into Kafka as a consumer of messages, right? Or PackRight becomes the producer, and also stream it to disk. So we still have the standard log level process going on, as you know and love. We have this new thing, the siphon, that's going off and doing it in real time. The other component, new component here, which many of you have probably never heard of, because it's internal, it's called Rat Soda. So I named my group, I named them Derp, and then I named this thing too. I really still think Brian's mad at me for these names, but Rat Soda stands for real time. I don't know what the A means. Structured Object Data Aggregator. The structure is important. So because we have AN message, we can do complex event processory things, right? Like deduplication, aggregation, joins, maxes, things like that. We can do all those things in a generic fashion, actually using reflection in C. And I can talk you through how that works a little bit. I don't want to give away too much. But we do this at very, very, very high volume, very, very high speed for all of the objects that we care to process this way on our platform. This is Rat Soda. a little bit about the join here. Because we understand the data model, right? And we have this very sparse join, and we have this very, very time-delayed join. We can play some tricks and sort of borrow some stuff from Kafka and borrow some stuff from some very interesting KV store technology coming out of Google with LevelDB or RocksDB, Facebook or LMDB. So what we have here is an append-only log of objects. So every single object that arrives at Ratsoda gets added to an append-only log, very, very fast operation. Just write to a log on the end. It's very easy to do. We compress and write every single record as it arrives. And we also make an entry into a memory mapped B tree that will give us the exact location of that portion of that join in a file and a key, right? So when then all the different parts of that thing arrive, we have simple separate read offset where we can jump into those logs in those different spots, pull the data out, make the join, and send it out in a real-time stream. Now the neat thing about this join is since it's so sparse, and since it's only transacted data, for all the rest of that sparseness, we just delete the files, because we don't need them. We pulled out all the stuff that joins over time. Once we get to the end of the time we want to wait, 12 hours, we just delete the files, because everything else is unjoinable. And we move on. We have a copy of it in HDFS, we have copies of it, but we don't actually need it for purposes of the join. The next thing that makes all of this work is a very, very simple Java complex event processor, which is separate. So Ratsoda will read your raw logs, your impressions, your win notifications, and your bids, join them together, and produce a new topic, which would be a standard feed for a member, right? We have another component here, like its only job is to read this new topic as things are produced. Apply the visibility profile on our platform so we don't expose information the buyer and seller maybe aren't supposed to know about one side of the transaction or the other, depending on who the member is pulling the feed. And then all it does is push. So it reads, applies profile, and push. In the push, we're initially supporting Amazon Kinesis. If you have Kinesis as your Kinesis user, we can actually push the stream at you very, very easily nowadays. And that goes off the platform. So Kinesis is what we support now. We may add support for, I don't know, someone else's Kafka cluster, some other cloud providers' data queuing system. We could easily add support for all this. We're sort of waiting to hear what people want to use, what people do use, and then we can add support for that going forward, so we can sort of aid adoption of this. So this is the whole picture now. We've got sell-side information, buy-side information going through PackRight, normal loop. We've got it pushed into Kafka, to the Ratsoda join. We've got the Java complex event processor, and it goes out. Now all of this, in the old way, is a 2-hour loop. All of this in the new way is on average 10 to 30 seconds, right? That's a big, big leap forward in terms of when you can get data to process it. So what? BFT, as they say. Why is this important? That's a great question. So some of you may be familiar with this as a pulse feature on our platform, which we had announced, I think, at Summit last year, I think. And this is the spark line of spend for a campaign over the last 30 minutes. This all is running basically on the same technology, where we spew off these rows, they go into Ratsoda for a quick aggregation, they go back into a complex event processor, the UI pulls it, and we draw it for you. It's a simple in-memory time series store. Here it is. That's extraordinarily useful. I wish I had actual data for you, I didn't get time to put it together. But I've heard so many stories of so many campaigns and problems solved by just being able to see what's happening, right? The old way when you would push things out and pray that you got all the targeting right and come back 2 hours later and go, oh my God, I just bought the internet, right? I'm gonna get fired. So we released this tool and a lot less people got fired, and that was good, right? But this is just an extension. We can now do this with any kind of data and not just spend. Another really important thing we could use streaming data for is real-time optimization off of our platform, right? You may decide that this curve looks really bad for CPM for you, and the spend drops after the start of an hour or the start of a day or whatever it is, and there might be some cutoff point for you. You can then stop your spend then, immediately. Just stop. Don't wait 2 hours later when you're wasting all these CPU cycles doing this spend on your own bidder, or let's talk about, I don't know, what's another example of this? Conversions, right? You may decide you're spending all this money trying to get these conversions, and you know at some point it's just not worth the money to try, that conversion is not going to come, because you know it happens in the first 12 hours of the first user IC or whatever it is. And so you can shut off spend because wasting money on trying to grab those conversions is a waste of time. Old platform, you couldn't know that until 2 hours later, right? So that's 2 hours of wasted money, which could be redirected elsewhere on maybe a different campaign with a different sort of conversion. You can also do health checks. This is Pulse's an idea of this. You can do health checks about your platform. So I think I have an actual example of this. Let me see if I can get it. Yeah. So this is live, coming off of a member's feed. I won't tell you who it is. I picked a few countries here in EMEA. We have Great Britain in red, Germany in green, Italy in light blue, and France in dark blue. And the top is transacted impression counts for this member per second. And the bottom is average CPM, right? And then the donut there is sort of the spread of impressions across the countries. So you can actually see, this is probably not a good example because I don't think anybody here really cares which country the things are serving in. But as an example, let's say you did care about that. And you came in one day and you expected a mostly green donut, and it's mostly red. That's a pretty big stop sign. There's something's wrong with your something, right? And now you can see it as it's happening, as right now. This is actually live right now. Oh, you can also do other cool things, like you can do these cool geo-visualizations. So these are impressions from a separate feed, grouped by latitude and longitude, right, and plotted on a map. So these are mostly mobile impressions where we get good latitude and longitude data. The bigger the circle, the more impressions happen at that spot at that time. Right? This is a 10-second aggregation where we're just grouping them together and plotting them. Right? This is pretty neat. This is really just a gimmick. This is not really useful for anything, but I think it looks cool. Right? And of course, we had the example earlier where you guys, well, some of you may have played. Fun and profit, right? This is, in order for this game to work, in order for this sort of silliness to happen, a lot of things had to happen, right? We had to have someone visit a website somewhere, have a tag, or maybe from a third-party exchange, have some kind of ad call come into the impression bus. We had to conduct an auction, right? We had to log out some information about that auction. We then had to wait some period of time for a win notification and log that out. Inform our bidder that we won, log that out, right? Handle those things through the PackRight system, join them together, spew it back up into Kafka, right, as a new topic. Have this, write a web app, we had to write a web app, thank you, Sweeney, to actually pull these things down, pull the creative ID out, re-render it, and draw it on the page for you to shoot with missiles out of Brian's head. There's a lot to that, right? And it's now all possible in seconds on this platform. So thank you for listening. If anybody has any questions about this or anything else that I can answer, shoot.
What's the average delay?
Average latency?
Yeah, the latency.
I said that a little bit earlier. It's between 10 and 30 seconds, depending on, most of that's buffering delay. Like so I said earlier, we have a trade-off here between throughput and latency. And because we have so much volume, we try to buffer up the buffers as big as we can. This is tunable for us. We can turn it down. We can turn the latency down at the expense of network bandwidth, right?
What's the depth of the backlog in Kinesis? So if I go down to my site and I'm listening to the queue, how long?
That's a good question. We can actually tune that per member. So right now we've been using a 2-hour default, but we can make that longer depending on expense and how many disks we have to actually store it on. But we've been using 2 hours to push. So if Kinesis goes down, you'd have 2 hours of backlog, and then you'd get it pushed back through. Sorry, we can wait for the mic so that everybody can hear the question.
Do you have any plans to open source any of the, like the PackRight or the rat soda?
Yes, I do. That's all I can tell you about that. questions, comments, desires for, oh, over here.
I'll just ask, for us to enjoy, it's only through the streaming APIs, only through the log level data, or will this data also be available on the console reports that will be
So,
or near real time?
I see what you're saying. So will we put, the question is, will we put this sort of real-time stream into quick stats or your quick reporting that you get now?
Or in the API?
Or available via API call? So I would say at this point, maybe. The difficulty there is there's a lot that goes into being the producer side of that equation, right? So if we have to support sort of thousands of clients all coming and wanting to pull their individual streams, so in other words, being a stream hoster, that's a different sort of problem. At this point, we do very much prefer to push, so we would prefer that you set up your own infrastructure to receive, and we will deal with some queuing and backlog and some high availability for your data stream. But we very much want to push it at you and not have you come get it, right? Now, as far as dashboarding, that's a whole separate question. I'd love to hear that you want that. You want dashboards like that available on the console. That would be a cool thing to build. So, over here. You can, I'll repeat it if you just want to shout. Oh, he's got it.
Hi. Is there anything in the roadmap for customizing the CEP, or is it at the moment that basically that stream is going to be just pooled, or is there any plans to maybe basically you could configure something in that CEP so we could maybe
Well, okay, what would you like to do? I guess I don't understand the question.
maybe, I mean, obviously things that you could do in Kinesis when you get it, but maybe you some alert or I don't know, some partitioning or something.
Oh, yeah.
Basically offloading to you, but it's.
So yeah, we will partition on any of the fields you want when we send you your feed, so we will definitely do that. I should have probably mentioned that. When we send to Kinesis, we will ask you, how do you want this split up? Say maybe by advertiser ID or maybe by campaign ID, I don't know. Whatever it is, we will split it up that way and send it into your Kinesis instance, split up that way. But as far as, maybe you mean customizing the fields that are in there?
Well, having the CEP, if there wasn't any language, I don't know.
Oh, you mean we run your code? Yeah, probably not.
That's some given language
I
or
don't know.
something.
Talk, there's a guy sitting next to you, ask him.
Thank you.
Another question, just to be sure that I understand, you receive notification only when you win the auction and at the moment that you win the auction, or about the moment that you win the auction?
Yep. So for third-party supply, for SSPs, yes. You have to actually get told on our platform, you won. Now for stuff that we manage, for our directly served tag-on-page stuff, we know we won or not, because there's no other party to the auction. So that stuff flows through instantly. The only time we have to pay the price of that time delayed join is when we are a third party to some other exchange, basically. There's a lot of questions. It's good.
Hi, just a quick question on your win rates. Can we get them as well in the log feed?
I'm sorry, say again?
The win rates from the log feed, can we get that back sent to us?
Win rate, you mean your own members'
Our win rates, right.
win percentage?
Correct.
Per auction?
Well, every impression that we had, so we have bids that you've placed on our behalf, and the bids that we've won.
Yep.
So can we get that ratio?
That would not be this standard feed, because that's more of an aggregation over time, I'm guessing. It doesn't make sense per impression
Of course,
to get
of
your win
course,
rate.
of course.
Let's talk about it. Find me and we'll talk about how we can make that work, because that sounds really useful. I don't know the details, but yeah, that sounds really useful.
I didn't quite understand why you'd be generating C code and not just using protobuffers.
So, you mean writing the protobuf data directly?
Yeah.
Instead of generating C code to write protobuf?
Yeah.
Because we want to use the protobuf libraries just in case there is a improvement or divergence in the way protobuf works. We could actually write the bytes, write the variable integers, right, ourselves, but there are pretty good libraries that exist for C that does it for you. So instead of writing the individual bytes, which would be slightly faster, We offload that to a library.
Or you could just use the Python library which does that.
Python,
Yeah.
no, we can't. That's way too slow. That won't keep up. Not at our scale.
Okay, because you're creating C code from Python and then C would be.
So no. So Python is a code generator.
It just creates a C code.
It writes C code out, and then we compile that.
Okay.
All right. So effectively, it's machine code at the end of the day that we're executing. It's machine code that calls into a library in Proto C, right? That is already highly optimized to do that.
Mm-hmm.
We could, in fact, write the protobuf bytes ourselves. Yes, and we do that in the case of native. I didn't put numbers in this presentation, but our native platform format is about 4 times faster than protobuf for serialization and deserialization. Pretty much about 4 times, 3.5 times. That's because we don't have to do any of this variable integer calculation, right? We waste a little bit of space for speed. So yes, we could there's some gains there. There's also plans to support other formats going forward. Like I'd like to support Thrift. I'd like to support Cat and Proto, if any of you have heard of that, as sort of components of this AN messaging library. And then I would like to just give it to you all to use. And that might be coming soon.
That would be brilliant.
Yeah.
Thank you.
How are we doing? Any other questions? It's really hard to see you guys up here. No? Good? All right. Well, thank you very much for your time.